At this point, I'd say it's time to wrap up the factors of sine and cosine examples and discuss a general strategy for integrals involving these. So for an integral of the form cosine to some power x times sine of some power x dx, well, if the factor on sine is odd, then we're going to preserve one factor of sine and then use the identity sine squared x equals 1 minus cosine squared x to express the remaining factors in terms of cosine. Then when we substitute, we can let u equal cosine x, and then du will take care of the remaining factor of sine, and we're all set. Then if j is odd, the same thing is true, we just preserve a factor of cosine, because that's the factor on cosine. So in general, we're looking for one of these two to be odd. And if that's the case, this is how we would approach it. But we also mentioned that it's possible that both of these end up being even. Well, if that's the case, then we have to use those power reducing formulas and reduce the degree and try again. Sometimes that will result in an additional factor that has an even degree. Sometimes they're all odd degree at that point. You just have to work through the algebra at that point to see what happens. Now, the other thing is that it's entirely possible that we have the situation where j equals 0 or k equals 0. Now, you wouldn't want both, because that would effectively just be the integral of 1 dx. But if an exponent is 0, something to the 0th power is just 1. So this doesn't rule out single factors of cosine to some power, or just single factors of sine to some power, as I showed in an example in the previous video. If you have even powers, I showed you how you could just take the even powers and split those up using the power reducing formulas. If you had an odd power, then effectively what you could do is preserve one factor, which leaves you with even factors remaining, change those using these formulas here, the Pythagorean identities, and then work the problem from there. So let's take a look at a couple more examples and show you what I mean in a few instances here. So I have one, evaluate the integral of cosine to the 8th of x, sine to the 5th of x dx. Now, based off of our assessment, we really want to focus on this factor of sine to the 5th x, because it's got that odd power. Because we have an odd power here, what we can do is rewrite this as sine of x times sine to the 4th of x, and I don't really need to write the dx here. So I would change this in that way, and I'm preserving one factor of sine x for substitution later on. But these remaining factors of sine to the 4th, I could write as sine x times sine squared times sine squared, which would be the same as 1 minus cosine squared x times 1 minus cosine squared x. And in that case, I can then distribute and multiply. So sine x times 1 times 1 is 1. 1 times negative cosine squared is negative cosine squared, but then I have another matching factor, so it's actually minus 2 cosine squared x. And then minus, well, no, negative times negative would be positive, so plus cosine to the 4th of x. Now, it may look like we have to start using the power reducing formula because we have these even powers of cosine. But we don't, because the thing is, we have this remaining factor of sine that we can use for u substitution. It's only when there are only even factors of 1 that I have to use the power reducing. So this problem can be rewritten as cosine to the 8th of x times, and I'm going to reorder these here, so times 1 minus 2 cosine squared of x plus cosine to the fourth of x times sine of x dx. And of course, this is getting preserved through du. And then the rest of this is going to get simplified just with letting u be cosine x. So one thing that I can go ahead and do is actually distribute this cosine through and express this as the integral of cosine to the 8th x minus 2 cosine to the 10th of x plus cosine to the 12th of x times sine x dx. And now I'm ready for substitution. So I'll let u be cosine of x. And then du, cosine has the derivative that's negative, so negative sine x dx. So what that's going to do is change my problem in such a way that I'll have a negative out front, but this will become u to the 8th minus 2u to the 10th plus u to the 12th, and then sine x dx is being taken care of with du, so then that's all times du. Now I can integrate, and let's see, this would be, I'll just say negative u to the 9th over 9. And I'm sort of distributing this negative as I go through, so this would be then positive 2 times u to the 11th over 11, and then minus u to the 13th over 13 plus c. And then, at this point, I'm all finished. I just need to simplify a little bit with coefficients and go back to what the value of u is. So I'll write this as negative 1/9 cosine to the 9th of x plus 2/11 cosine to the 11th x minus 1/13 cosine to the 13th of x plus c. And there we have it. So you can tell that this problem got a little bit more complex because there's more terms in the end, and that will happen the larger this odd power is. So if this was sine to the 7th, I would have had to split this up as sine x times sine to the 6th, which would have given me 3 binomial terms to multiply out. So it's just going to get more and more difficult with a larger odd power, but the process is the same. Now here's one more of this type, which looks rather difficult, but the thing is, it just kind of reinforces that as long as you have an odd power of one of these functions, then you're all set. It's actually not that bad to work through. So for instance here, I have the square root of cosine x times sine cubed x, which, don't be scared away by the square root, because that's really just an exponent. It's an exponent of 1/2. Now, I'm unaware if rational values are defined as even or odd. It's my understanding that it's just integers defined as even or odd. So, but it doesn't really matter if this is even or odd, because we have this odd power over here that we can work with. That's all we need, is one of them to be odd. The other exponent can be anything. So what will happen here is we'll start off preserving one factor of sine. So this will be cosine to the 1/2 x times, we'll go ahead and make this sine squared x times sine x dx. Change that sine squared into cosine squared. So cosine to the 1/2 x times 1 minus cosine squared x times sine x dx. Distribute the cosine to the 1/2 power. So this would be cosine to the 1/2 x minus cosine, so this could be written as 4/2, so squared is the same thing as 4/2. And when you multiply exponents, you can, well, if you have two bases that are the same, you can combine them into a single exponential function by adding. So 2, which is 4/2, plus 1/2 would give me the 5/2 power of cosine, and then times sine x dx. At which point I can freely substitute. I would just let u be the cosine of x. Du is negative sine x dx. And what will happen when I substitute is I will get the integral, well, I should pull the negative out front to start with. So negative integral, this would be u to the 1/2 minus u to the 5/2, and then sine x dx is taken care of with the du. And for simplification, I could actually distribute this negative and then just make this one a negative term and then this one a positive term. That's okay, I'll do that in the end. For now, let's just go ahead and integrate. So this would be u to the 3/2 over 3/2 minus u to the 7/2 over 7/2 plus c, and this will become negative 2/3 u to the 3/2 plus 2/7 u to the 7/2 plus c, and when I plug back in for cosine, I'm going to have negative 2/3 cosine to the 3/2 of x plus 2/7 cosine to the 7/2 of x plus c. And then I'm all finished.